Welcome to NEXTED by Nexaspaces Tech Education. In today's session, we're diving deep into the fascinating world of microcontrollers, the brains behind modern embedded systems. Whether it's a smartwatch, an industrial sensor, or a home automation system, there's a microcontroller working behind the scenes. In this video, we'll cover what a microcontroller is, how it works, its internal architecture, key components like CPU, memory, I/O, and timers, a quick comparison with microprocessors, and practical real-world examples. So, let's power up and get started. A microcontroller is a compact integrated circuit designed to perform specific operations in embedded systems. It contains a CPU, memory, input-output peripherals, and communication interfaces all on a single chip. Unlike general-purpose processors, microcontrollers are optimized for specific control tasks. Think of it like this: a microcontroller is the control system of a washing machine that handles the motor speed, water intake, and timer, all in one. Let's now look at the architecture of a microcontroller. Most microcontrollers follow either a Harvard or Von Neumann architecture. The Harvard architecture separates instruction and data memory, allowing faster data access. Regardless of architecture, a typical microcontroller consists of these blocks: CPU core, flash memory, program memory, SRAM, data memory, I/O ports, timers and counters, ADC or DAC, and serial communication interfaces. The CPU is the brain of the microcontroller. It fetches, decodes, and executes instructions from the program memory. The CPU includes ALU, arithmetic logic unit, registers, control unit, program counter. The control unit directs how instructions move through the system. The program counter keeps track of the next instruction. These all work together to ensure tasks are performed correctly and timely. Memory is vital in microcontrollers. Let's break down the types. Flash memory, non-volatile, stores the program code. SRAM, static RAM, volatile memory for variable storage during execution. EEPROM, non-volatile, used for storing small data like calibration values. Flash is like your microcontroller's long-term memory, while SRAM is like short-term memory used while it's running. Microcontrollers interact with the world using input-output, I/O, ports. These are programmable pins that can be set as digital inputs or outputs. You can connect sensors, LEDs, motors, displays, and much more through GPIO. Some ports also support PWM for variable output control, great for dimming LEDs or controlling motor speed. Timers and counters are internal peripherals used to keep track of time or events. Timers generate delays or measure time intervals. Counters count external events like pulses. Timers are essential for real-time systems where timing is everything, like controlling a robot arm or maintaining baud rate in communication. Microcontrollers often need to communicate with other devices. This is where serial communication interfaces come in. UART for serial terminals. SPI for high-speed communication with peripherals. I2C for connecting multiple devices with just two wires. CAN in automotive systems. These interfaces allow microcontrollers to work in networks or with sensors, displays, and external memory. Let's clarify the difference between microcontrollers and microprocessors. A microprocessor needs external memory and peripherals to function. A microcontroller has everything integrated into one chip. Think of the microcontroller as a self-contained system, while a microprocessor is part of a larger computing setup. Where do we see microcontrollers in action? Everywhere. In smart agriculture sensors, home automation systems, medical devices like pulse oximeters, wearables and fitness trackers, automotive ECUs, drones, robots, and industrial controllers. The flexibility and low power of microcontrollers make them ideal for IoT and embedded solutions. Microcontrollers are programmed using C/C++, or even Python, like MicroPython. Tools like Arduino IDE, STM32Cube IDE, Heal Vision, Platform I/O are used to write, compile, and upload code. Developers use these tools to build logic, read sensor data, control actuators, and enable connectivity. In our next videos, we'll work hands-on with microcontroller boards like Arduino Uno, ESP32, and STM32, exploring how to blink LEDs, read sensors, and build mini projects. So stay tuned as we bring theory into practice. Let's quickly recap what we've learned today. Microcontrollers are integrated control chips used in embedded systems. They include CPU, memory, I/O, timers, and communication modules. They follow Harvard or Von Neumann architectures. They power everything from wearables to industrial machines. If you found this lesson useful, don't forget to like, share, and subscribe to NEXTED by Nexaspaces. Leave your questions in the comments. In the next episode, we'll explore popular development boards and how to start building embedded applications. See you soon.